Yeah.
It's the first class I've been
That's the
to.
forecast.
Seriously?
I didn't have first walk because I got plenty to go, and then I didn't go second.
You know?
Well, I'm glad you made it. How about that?
I'm for you, Bert.
It's like the weather boy, you're
Yeah.
lying to me.
Oh yeah.
Okay,
Oh wait.
what?
Eli was trying to rat you out in speech.
Huh?
Eli McGriddle.
What about it?
Oh, because he was talking about, he told Mrs. Piper, he's like, yeah, Mr. Burkant called me fat.
Called him.
He told him that, and so I had to explain to Mrs. Piper it was all in good fun, and that's because Eli insulted you. Like, he's like trying to rat you out, Mrs. Piper.
Oh, please.
Yeah.
You called him fluffy. You
I
called
say,
him fluffy.
I call that,
Not that.
we have it on film.
We do.
Okay, we
do.
have it on film. The evidence will clearly show that I called him
Fluffy
fluffy.
can be many things. It can be nice,
Yeah.
comforting.
Soft.
Like a sheep.
Yeah,
I mean-
sheep is fluffy.
Meant to be
Yeah.
sheared. I mean, Eli is soft. He needs a good
He is
shearing
soft.
like a sheep.
I mean, there's no denying.
Video evidence.
Dude, Eli's soft.
Yeah, that's like saying the
Yes, yeah, we're
sun
going.
is yellow.
Yeah,
We're going.
we're going. We're clean. This is going on YouTube.
All right, so, anybody have any questions on the lab? Yes, great.
The whole backside.
Dude, come on, man. Joel explained it so well to us.
Okay.
Come on, man. I explained it so well myself.
Now, let me explain my thought process and why I chose these specific masses. So you got a 200 gram mass hanging here, and you got a 240 gram mass, right? Now, I swear to you, the test coming up on Wednesday, if you are incapable of thinking through how this process works and how it's going to play out, before you even touch a formula, the test on Wednesday is going to be an unmitigated disaster. Okay, I'm going to tell you this right now. If you are incapable or unwilling to think through a problem before you even look at that equation sheet, the test on Wednesday is going to be an absolute train wreck. Okay, I'm going to tell you this right now. It is going to be a train wreck. But if you step back and you look at the problems, you'll notice that every one of these problems works the exact same way. They all start with the idea that either this thing is going to accelerate or it's not. So let's just start with this question number 10, with the basics. What am I asking you to find? An acceleration. So right away, what do you know the net force is not going to equal? Zero. So right away, hey, I know I'm going to have a net force that isn't equal to zero. At the end of the day, to get that acceleration, when you find your net force, what are you going to divide that by?
Mass.
Which mass? Total mass. Total mass. You always, always, always divide by the total mass. So at the end of the day, you know you're going to take some net force and divide it by how much mass? In this situation.
4 kilograms.
So I know I'm going to take some net force and I'm going to divide that by 0.44 kilograms. Okay? I know at the end of the day, this is going to be my last step. So what's the challenge? Finding the net force. Okay, right. Now, do you think this answer is going to be more or less than 9.8 meters per second squared? Allowing for the lab that you all just did.
Less.
Why?
Because you have something resisting the pull of gravitational acceleration, so it's going to be slowed down.
Yeah, so you know when you find this answer has to be less than 9.8 meters per second squared. Okay? If you get 9.8 meters per second squared, something has gone horribly wrong. Worse yet, you get something bigger than 9.8 meters per second squared. You were living like in an anti-gravity field where it like pushes it down. Okay? So then ask yourself this. What's the source of the force that's going to make this whole thing move? Honus.
The force applied.
To what?
To what? So the force applied from the 200 grams, that gram mass hanging on the string, is making it all move.
Being pulled by?
Gravity.
So leave out the 240.
Mm-hmm.
Can you find the force acting on a 200 gram mass?
Yes.
What are you going to do?
Multiplied.
0.2 by what?
9.8 meters per second squared.
Which is
The acceleration due to gravity.
beautiful. And don't tell me, oh, I'm gonna multiply 0.2 by gravity. Flip out, okay? So this is 0.2 kilograms. So you got 1.96 newtons of force acting down. Okay? Now, is gravity pulling down on this? Olivia, is gravity pulling down on the 240 grams?
No. Yes, because it's attached to that other weight.
Oh, so gravity's pulling down here, true? True? But what's the table doing?
Pushing up,
Table's pushing up.
force normal.
We're providing that force normal, okay? So, start with a chart. When in doubt, chart it out. Here's your force net, right? I don't know what it is, but I know I have to divide by 0.44 kilograms at the end of the day, right? So I'm going to have some FAP, I'm going to have some FOP, and I'm going to have some FNET, right? So, are you told anything about friction?
No.
No. I've not given you the coefficient of friction, I've given you nothing. So here's the most common misconception that you all have. You all want to go, well, this is an opposing force. It's not an opposing force. There's nothing happening up here. Does this mass resist acceleration?
No.
Sure it does.
Well, yeah, but
It has mass. It wants to stay there. Mother Nature is lazy. This 240 gram doesn't go, oh, pick me. I will just run in the same direction without a force. No.
trying to say
Hey?
there's no friction.
You got it. Something has to happen to this. So what's going to make this 240 gram mass move? This string being pulled down at 1.96 newtons. This is the only game in town to make this thing move. Now, so your applied force is going to be 1.96 newtons. So here's the deal. This is not an opposing force. Does it have inertia? Yes. Does it want to remain at rest? Yes, but inertia is not a force. So don't sit there and go, oh, my opposing force is 240 grams. No, it's not. How we take that into account is by dividing by the entire mass. This is where this is taken into account, by dividing by the entire mass. So, I got FAP at 1.96 newtons. Is there any opposing force?
No.
No. So what's your net force?
1.96 newtons.
There you go. And divide that by the total mass, there's your acceleration. This should make a pretty good GPA.
Yeah.
Yeah.
Yeah, and that'd
Yeah.
be weighted, wouldn't it?
Yeah.
Yeah, a weighted, pretty good weighted GPA. Okay?
This jacket is hard to take off.
You just put it on when you came in here.
I know, that's because I was cold then, but now I'm not.
Okay. I have that effect on me. Okay. Just, what?
I have a question, what we should do, I feel like we should do, number 14.
Okay, we'll get that.
We're still going, that's fine, I won't stop, we're still going.
Now,
Yes.
let's say we go back to this problem where we've got a 200 gram mass suspended from the end, okay? And we're going to make a chart of acceleration versus mass that's on the table, okay? All right, so let's think about what this graph is going to look like. So let's say that we've got a 240 gram mass that's up here on the table, okay? And then we'll go to an extreme case and have like an elephant, okay? And then a rhino, okay? So we could have, this is the mass that's up here, not what's suspended from the end, okay? The mass that's up there, right? So we got 240 grams rhino hippo, excuse me, rhino elephant. What's that graph going to look like? It's going
You,
Mary? When are you going to have your biggest acceleration of the system? When there's a 240 gram mass up here a rhino or an elephant?
When you have the 2.3 gram mass.
That's when you're going to have your biggest acceleration, right? Which we said was going to be what, 4.45 meters per second squared? So if I put a rhino up here, what's going to happen to that acceleration?
It's gonna go down to like almost nothing.
Bigger or smaller?
Way smaller.
Right? So if you consider this to be 0, and let's say this is 9.8 meters per second squared out here. So here's 9.8. This is your free fall acceleration. Here's 4.45, right? So a rhino is going to be where? Okay, somewhere in here, right? What about an elephant? Even smaller, right? So it's going to go something like this, right? Now, what's the only time you can have an acceleration of 9.8 meters per second squared?
There's no force opposing.
If there's nothing up here, because then your net force is
Just the acceleration.
1.96 newtons, divide that by 0.2, you get 9.8. So, will this eventually go to 9.8? Yeah. Okay. So, as you put more and more mass on here, the acceleration is going to become smaller and smaller and smaller. Now, what if we did this? What if we did a graph of applied force versus acceleration? Okay? So in other words, if no matter what I put up here, now let me change that up. Let's put applied force and mass on table. Okay? Let's change it up. So let's look at a graph of applied force here, keeping this constant and the mass on the table. So as the mass on the table gets bigger and bigger and bigger, what's going to happen to my applied force?
The same, more and more the same. It should stay the same, shouldn't it?
What's going to happen to the applied force? What creates the applied force? The 200 gram mass out here. If that never changes, then what's going to happen? It's going to stay the exact same. Nothing's going to change. As long as I keep a 200 gram mass out here, this is just going to be the same at 1.96 newtons. Because this has no bearing on it. Okay? You have to look at what is a factor in the calculation. This mass up here has no bearing whatsoever on the applied force of the system. Put an elephant, a hippo, a rhino, whatever you want up here, it's not going to make any difference. There's still only 1.96 newtons of force to accelerate that system. Now, what if we swapped it out? What if we put an elephant up here, took the elephant from here, put the elephant here, and put the 200 gram mass up here? Then what would happen to the acceleration?
It would increase a lot.
No, it would increase a lot. Okay? Even though it's the exact same mass, you're going to get a completely different acceleration. Okay, cool with that. Everybody understand? Now, this is a situation where if let's say you got to number 10 and you had no idea how to do number 10. Go back and look at the very front page. Look at the calculations that you did on the front page. This is why you write stuff down. So you can go back and go, oh, we did this in class. How do we get the net force at the beginning of the lab? Oh, we took that 10 gram mass and multiplied that by the gravitational acceleration, and then we divided it by the total mass. It's the exact same process here. Now, when you get to number 11, okay, all I'm asking you to do on number 11 is come up with the generic way to work this problem if there is no mass, if there is no friction. So you have two masses involved. You can call this mass 1, you can call that mass 2. You can call that mass 1, that mass 2. This mass alpha, this mass gamma. I don't care. Hanging table, I don't care. So you're going to set up a key and you're going to go, okay, here are the two masses that are involved. Okay, I don't care how you differentiate them. I honestly don't. But then you're going to tell me, okay, to get any calculated acceleration, I'm going to take this times something, and then I'm going to divide it by something else. And so all I'm trying to get you through is the algorithm, the thought process that's going to allow you to come up with any acceleration. And you lay them out. Just don't say, oh, m times g. Well, which m? Is it the mass up on the table? Is it the mass that's hanging? Or is it the combined mass? So lay that out. And if you're not sure, look at how, go to the front page. Look at how you did the front page calculations. Now, when you get to number 12, okay, I give you the coefficient of friction. Here's what's important. And you have to understand this. And I promise you, there's going to be a problem like this on the test on Wednesday. It will be the last question on the test. I'll even tell you where it's going to be. You have friction here. Does the mass of this have any impact at all on that frictional force? No. You could have an elephant tied out here. It doesn't make any difference. But here's the deal. You're trying to drag this thing in this direction. Which direction is your frictional force going to act? Vonda, I'm trying to drag this thing this way. Which direction is friction going to act?
The opposite way.
Yes. So now, when you look at FAP, by having friction, does that alter my applied force? No, it doesn't alter your applied force. What's the only thing you need to calculate that applied force?
Weight
Of what?
or mass of.
Yes, if there's friction up there, guess what? Gravity doesn't know, gravity doesn't care. Okay? Gravity says, wow, here's the mass. I'm going to pull it down. Cool. Doesn't matter what's going up there. Okay? This has nothing to do with the applied force. Does it create an opposing force?
Yes.
Yes.
Does it alter your net force?
Yes.
Yes. But it has nothing to do with your applied force. You have to be able to differentiate what is a factor in each calculation. If there's friction up here, it does not alter this calculation at all. Nothing to do with it. Now think this through. This is why I said you have to be able to think through a problem. If there's friction, what's that going to do to the acceleration of the system? Slow it down, right? If there's friction, does it alter your applied force?
No.
No, but what does it increase?
Opposing force.
Your opposing force. So what does it do to your net force?
Makes
Brings
it
it
smaller.
down.
Makes it smaller. Because now you have to pay the friction mafia. Okay? Once you pay the friction mafia, what happens to the money that you have left over?
Smaller.
Becomes smaller. What happens to your acceleration?
Smaller.
Becomes smaller. Okay? So your acceleration on number 13 should still be a pretty good GPA. Okay? Should still be a pretty decent GPA. Now, let's talk about 14, Jones, shall we?
Yep.
Okay. Now, you'll notice, here's what I want you to look at. When I typed up this problem, and by the way, it was noted in first block that if you try and Google the answer keys to this, you can't find them. Somebody in first block tried. So it's like, I wrote it all. It's not out there. It isn't like it's a textbook. So, when I type this up, notice that I use the exact same masses of 200 and 240. Okay, so the masses are going to be the exact same. That's why I chose those numbers. Now here's what's different. On the first problem, you had a 200 gram mass here and a 240 gram mass here. This is why I set this up the way I did. Can a 200 gram mass accelerate a 240 gram mass that's up on the table? Yes. In this situation, 200 gram can drag a 240 gram. Okay? Now, when you get to 14, here's the setup. 14 is an Atwood machine, which is what the lab that I just gave back. Atwood machine is a single pulley, usually, and you've got a 240 gram mass on one side and a 200 gram mass on the other. Now again, you've got to be able to think through the system. Do not get wrapped up in the math. Do not even touch a calculator. Just think the problem through. It's a Zen thing. Become one with the problem. Okay? Crouching physics. I don't know what you call it. So here's the deal. Just look at this. Which direction is this thing going to go when you let go of it? 240 is going to go down. And the 200 is going to go
Up.
Is it going to accelerate?
Yes.
Is there going to be a non-zero net force?
Yes.
Yes. At the end of the day, how are you going to get your acceleration?
You have to
What's the last calculation you're gonna do?
Net force divided by
Take the net force divided by what?
Total mass.
Total mass. So this is what's similar. At the end of the day, I'm going to take some net force and I'm going to divide it by 0.440 kilograms, which is the exact same step that you did up above. That step's going to be the same. But here's the difference. If I've got a 240 gram mass here and a 200 gram mass over here, 200 gram mass isn't going to drag up the 240. The 240 is going to drag up the 200. Okay? So here's the difference. You say this is going to pull this thing down, and it will, and it's legitimate, and it's a beautiful observation. So if this is 240 grams, what's the gravitational pull on a 240 gram mass? What are you going to do?
Multiply 9.8 meters per second
Yeah,
squared.
I want to take 9.8 meters per second squared times 240. What do you get? 2 something.
2.35 newtons.
What'd you get? 2 point what?
235.
2.35?
Yeah.
Yes.
Newtons. That's the force that's pulling down. How much force is pulling down on the 200 gram mass?
1.96.
1.96 newtons. So this is pulling down at 2.35. That's being pulled down at 1.96. It's a tug of war. Who's going to win?
2.35.
By how much?
Right. 0.39.
Yes. Guess what? That's your net force. Wow. What are you going to do with that net force?
Divided by total mass.
Divided by the total mass. It's the exact same problem. Okay? The only difference is that 200, all I did, if you think about this, in the first problem, I had a 240 gram mass up here. Okay? That's what I did. I had that up here. And the 200 gram mass could pull it down because its weight was being balanced out by the table. Over here, that table was gone, and now the 240 is going to drag up the 200 grams. See the difference? We're cool. Very good, Mary?
Yeah.
Okay. Did I take some pressure off you answering questions?
Yes.
Okay. That's what I do. Okay.
The least precise
So
decimal,
the
which is supposed to be the hundredths place, so you
2.2505.
can't have that zero on the end.
Wait, or am I just thinking?
Yeah, the bigger mass,
As you apply.
the bigger force you call your applied force.
Yeah.
This one is opposing that motion, so make that the opposing force. But make one of them positive and one of them negative. We're just subtracting out. I don't care. It's the same idea. So this is what you're trying to do. This is what you have to pay the gravity mafia. The difference between the two is what you get to keep.
Sorry, I'm out of it.
It's okay. I feel the same way. So we're going to do that for some of my freshmen today during on. Anyway. Okay. That was more like, okay.
Are they scared of you?
A little bit, yeah. If they're nice, I let them breathe.
Oh, okay.
If they're nice.
What is it, $1 per second to breathe?
No, it's just, no.
Is that how you raise your?
No. It's just. Yeah, that's how
you get so
how
much
we're gonna fund
money.
the solar project. We'll let the freshmen breathe. Seriously though, I think mom would, some of them wouldn't pay the freight. And I don't blame them either. It's like, whatever, it's Timmy. Okay. Any other questions on this? We're good? Once, twice, sold? Give those handed in. So,
Cut my hair.
Are you getting the action shot?
Action shot.
okay,
Please put in
so,
shaky cam.
so here's our last big topic before the test coming up on Wednesday. So here I've got yonder cart, right?
Yeah.
And if I do this and I move it back and forth, what does the cart do?
Tries to stay in the exact
place.
same position.
Stays there. Why?
Because there's very little friction and it has inertia.
It has inertia. What does it want to do?
It wants to stay in the same
It wants to
place
stay still until
until a force is applied to it.
outside force acts on it, right? Now if I flip it over though,
Oh, that's good.
not near as cool.
Track.
What's changed? Have I changed the inertia of the cart?
No.
No.
No. Why haven't I changed the inertia of the cart?
You have to
You didn't
change
change the mass.
Because it's the only thing that affects inertia,
Mass.
mass. But what's different though?
the friction.
There's friction. Now when I move the track,
It goes
there's friction that's gonna make it
Move.
go with it, right? Does it want to move?
No.
No.
It still wants to remain stationary, but there's friction that's gonna make it move. Okay. Now, if I put this down, hold on. And it's perfectly flat, why doesn't it accelerate?
Because there's no.
Is it because there's no forces acting on it, or because there's no unbalanced forces acting on it?
There's no unbalanced forces.
Okay?
Is that?
So, when this is sitting there on a completely flat surface, and a pin that I can't find, I got too much crap here. So, on a perfectly flat surface, I got gravity pulling this thing down, and I got my normal force pushing up on it, right? No worries. But if I take this, and I give it just even the slightest bit of incline, and let go of it, what do you notice?
It accelerates.
Accelerates. Now, here's a very, very important yet crucial idea. Which direction, it's simple, but bear with me. Which direction does it accelerate?
Downward.
Down the inclined plane, right? If I do this, I'm going to say, here, class, this is the lab that you're going to do. You're going to take an inclined plane, you're going to lift up one end, and you're going to let go, and you're going to observe what happens. And then you're going to push it back up, and you're going to let go of it, and you're going to observe what happens. Now, why am I not going to have you do that?
Because we know
Because you know what's going to happen. Is there a chance that you're going to let go of this thing, and it's going to start going up the hill?
I mean,
There'd have to be some other force acting on it.
Yeah, there'd have to be something else acting on it, right? Because if I do that and let go of it and it starts to go up the hill, you're going to be like, ooh, it's magic, okay? Right? He's a wizard, right? Because every time I let go of it, this thing goes down the hill. Now, if I lift it steeper, what happens to the acceleration?
increases.
It increases. Oh, right. Right. So, here's what's important. Every time you let go of it, Mother Nature's trying to take it down the hill. Why does it take it down the hill? Mary.
Because of gravitational acceleration.
It's true. But there's a deeper truth. Why doesn't it push it up the hill? Because what? What'd you say, Johns?
The opposing is bigger than
Oh, God, you gotta speak louder, honey. I can't hear a word you say.
I feel like I'm wrong, that's why. Okay, the opposing is bigger than the applied force. That's why it's going down. Or is it opposite?
There's no opposing forces. I'm just letting this thing go and it's just gonna roll. There's no opposing forces. We're not pushing it, pulling it, anything like that. It's a deeper truth. Why does it go down the hill? Mother Nature is lazy. Guess what? Mother Nature goes, it's just too much effort to push it up the hill, right? It's going to go to a lower energy state. You let go of it, it's going to go in that direction. I'm guessing some of you have gone snow skiing. When you get off the ski lift, do you worry about gravity pushing you farther up the hill?
No.
No. Okay? No, you're not going to go higher up the hill when you ski, when you get off the chairlift. You know gravity is going to pull you down the hill. So look at this. So when I put this thing on an incline, okay? Now, this is going to work out nicely with the math. Let's say the mass is 1.02 kilograms. So to get the weight, we're going to take that times 9.8. Trust me, you get 10 newtons. Okay? So gravity is trying to take this. Gravity is trying to pull this thing towards the center of the earth with the force of 10 newtons, right? So now here's what's important, and this is another absolute truth. when I drop this tennis ball, every time I drop that tennis ball, which direction is it going to fall? Golf ball, whatever. Whatever. Neither one of them are right.
It's gonna fall down.
Okay? Which direction is it going to fall?
Down.
Down. Straight down?
Yeah.
Technically towards the
Center of the
center of
earth.
the earth. Why does it take that path?
That's where gravity.
It's lazy, right? Now, if I let go of it, and all of a sudden the ball started to go like this, gonna happen?
No.
No, unless there's wind.
Unless there's a lot of wind,
Yeah.
okay? But inside the confines of this room, I let go of it, every time it's gonna fall straight down. That's the direction of the force, right? So your acceleration vectors only point in the direction of the unbalanced force. So when I let go of this cart, here's what's happening. Gravity is trying to pull this thing straight down. But what's preventing it from falling straight down? The slope, the surface is, right? Okay? Now, when I take this golf ball, Gary the golf ball, and I put Gary the golf ball right there, is gravity trying to pull Gary the golf ball towards the center of the earth?
Yes.
What's preventing it from doing so?
The table.
Table, which is providing a
Force normal.
force normal, right? Which direction does the force normal act?
Up.
Up. Now, technically, it's acting at a right angle to the table. Okay? Technically, that's the direction that it's happening. So, when I take yonder cart, right, and I put it on yonder ramp, what's gravity trying to do?
Pull it down.
Gravity's trying to pull it straight down. But what's preventing it from falling straight down?
Force normal.
The normal provided by the ramp. So the ramp basically says, I'm still going to let you fall, but I'm not going to let you fall straight down. Is this cart still eventually going to end up on the ground?
Yes.
Yeah, but it's just going to take the long way to get there, right? It's still going to take the path of least resistance. So this thing wants to fall straight down. So the normal force is acting at a right angle to this surface. The normal force in this situation is keeping this cart from falling straight down. So gravity is still pulling it down, but we're going to take that gravity and make it go down this way. So the normal acting here makes gravity act down this way as opposed to acting straight down in terms of how it's going to make this thing move. So I got this acting straight down. Clearly, I've got some force that's acting down the inclined plane. And this is what we're going to call force parallel. Okay? Don't look at this and go, oh, that's force 11. Okay? It's not 11. That just stands for force parallel. So, I've got this acting straight down. I've got my force parallel acting like this. But then, here's the importance of this surface. This surface is preventing this from falling straight down. So this is what we're going to call our normal force, which is going to be at a right angle to the surface. Logan, do you have a question?
No?
Okay, all right, I thought you said have that. So, your parallel, oddly enough, acts parallel. It's a radical concept, I know. Your normal force is going to act at a right angle, and gravity always acts straight down. Normal does not act straight up. It acts at a right angle to the inclined plane. So on any force or problem involving an inclined plane, there are always three forces that you want to find right away. A gravitational force, a parallel force, and a normal force. You always start with those three. Now, the next question is, but Mr. Burkamp, how do you calculate force parallel and force normal? Oh, good question. Okay, now I'm going to draw this a different way, okay? I'm going to draw it a slightly different way. So, I'm going to redraw this, and I'm going to work off of a 30-degree angle because it's going to make the trick easy. So I got a 30-degree angle, and we're going to use the same mass on every one of these so we don't have to recalculate things. So we're always going to use a 1.02 kilogram mass. If I multiply that by g, trust me on this one if you don't, you're going to get 10 newtons. Now, I'm going to shift where these vectors are drawn. I'm going to draw that normal force right here, okay? So there's my force normal, okay, acting at right angles to the surface. Then I'm going to draw my parallel force acting down. Change. There's my force parallel acting down this way. So what that means is that this makes a nice little right triangle. Oh, how cool is that? Okay. Now, what you will always know is your gravitational force. Why do you think that's the easiest one, and why do you think that's the one you will always know? What's the only thing you have to know to calculate FG? Mass and the gravitational field of whatever rock that you're on. Okay? Our rock has a value of 9.8. Okay, easy peasy, take 1.02 times 9.8, boom, rock to the races. Okay? So, now if you go through the trig and the geometric proof, whatever angle this is here is going to be the same angle here. Okay, so that's what makes this simple. If this is a 30-degree angle, this is a 30-degree angle. So if you go through like alternate interior angles and all that good stuff, you can prove that this is a 30-degree angle. Take my word for it, it's 30 degrees. Now, the gravitational force represents the hypotenuse. I want to find the side opposite of that angle, knowing the hypotenuse. So, what trig function is going to get me the side opposite, knowing the hypotenuse and knowing that angle? Sine or cosine?
Sine.
Why?
Because sine is equal to the opposite over the hypotenuse.
Okay. So the sine of theta is going to equal my adjacent side, excuse me, my opposite side, force parallel, over FG. So, bonding. How am I going to get force parallel by itself?
You have to multiply by FG.
So I got FG sine theta equals force parallel. So if you look on your big dog equation sheet, this is here. This is where it comes from. Okay? It's a simple trig function. Okay? FG sine theta. Now, what about the normal force? So if I use sine to get this one, Olivia, what am I going to use to get my normal force?
Cosine.
Beautiful answer. Why?
Because you have adjacent
And the
other thing. The angle.
the angle, the other thing.
That one.
Yeah, that too. Okay. Yeah, kind of have to have three things. So this is going to be cosine. So force normal is going to equal FG cosine theta. Oh, that's kind of cool, right? So look, this is what I introduced at the beginning in terms of force normal, and this is where it comes from. It's from this triangle right here. But here's the cool thing. Let's talk about trig functions and values. If this thing is flat, okay, if this thing is perfectly flat, what's the angle going to be?
0.
So, here's my question. Except for Honus, because I'm tired of hearing Honus answer the questions.
Yeah.
Great. What's the sine of 0 degrees?
Let me think here. 0.
0. So on a flat surface, how much force parallel do I have? 0. Guess what? Things don't roll on a flat surface because there's no force parallel. Oh, how cool is that? Now, what's the cosine of 0?
1.
1. So on a flat surface, Fn equals Fg, right? Okay, on a flat surface. Now, if you go to the extreme, let's go 90 degrees. Because go big, go big or go home.
I agree.
Let
So,
it go.
on a 90-degree angle, okay,
Ooh.
Whoa.
cat-like reflexes, okay?
Wide receiver. Tony, you should get one of those.
So, on, if this, feel like a lumberjack. I'm a lumberjack, I'm okay. All right. So, on a 90-degree angle, what's the sine of 90?
1.
1.
Yeah.
So on a 90-degree angle, the force parallel is your Gravitational force. Oh, how cool is that? Now, if this is a 90-degree angle, how much of that weight is acting into the board? None of it.
Goose egg.
A goose egg. Because it's all acting down. What, you make it sound like...
Yeah, I know, make it funny.
I've never heard that.
Really?
You've never
You've heard it from him like 10 times.
Really?
Yeah. Probably in the last 2 or 3 weeks.
Shows how much Nick pays attention.
Yeah.
Must be what?
Us Europeans don't use that term.
Stupid.
A goose egg? Like you guys don't have goose? Or geese?
That's Canada.
Or, that's Canadian. Okay. All right. So, got that idea. Now, we're going to go through and we're going to start working with some numbers. So, I'm going to redraw this. Clear the board. And all of these we're going to put with 30-degree angles so that we don't have to redo the calculations each time. So, we've still got a mass of 1.02 kilograms. FG is still going to be 10 newtons. Now, I don't care how you draw the force parallel and the force normal. You can either draw it as a triangle here, or you can draw them in the actual places that they're going to act. If I had a preference, I'd have you draw it this way, because that shows the actual places as like a free body diagram. But if you like trig functions and being able to see that triangle, and that makes more sense to you, draw it there. Okay? I don't care. I'd give this a slight nod, but I'm not that particular. So, the last one I've got is your force normal. Do not draw this force normal straight up. It does not act straight up. Okay? That force normal acts at a right angle to that surface. So, the first thing that you do is you calculate this gravitational force. Do not worry about making this negative, just get a number. Okay? This is a gateway force. Okay? All that's going to do is lead you to the force normal and the force parallel. Okay? So just get this number and then you never speak of this number again. It's dead to you. Okay? You just use this to get these numbers. So, how am I going to get my force parallel knowing that this is a 30-degree angle and the gravitational pull between this and the rock that we're on has a value of 10 newtons?
Just multiply by point.
So I'm going to take 10 newtons times the
Sine
of, and you're going to get 5 newtons. Now, here's the most important decision that you have to make on any force parallel problem. And there is no right or wrong decision. Okay? But you have to make a choice. You're going to have forces going up this inclined plane and you're going to have forces going down this inclined plane. You need to decide how you want this to play out. Do you want down to be negative? Or do you want down to be, or do you want up to be negative? There are no right or wrong answers. It makes me no difference whatsoever. Tori, how do you want this to play out? Do you want down to be negative or do you want up to be negative? You're down to be negative. Okay. So, on the TCS, the Tori coordinate system, okay, this is what we're going to go with this problem. On the TCS, we're going to define down as being negative. In first block, they chose down to be positive, okay? Equally valid. I don't care. It makes me no difference, okay?
Which is easier.
It doesn't make any difference. Literally, the math is the same. I don't care. If this makes sense to you to define down as negative, go with it. If you want down to be positive, it doesn't make any difference. It's the same math, it doesn't make any difference. So, in the TCS, this is going to be a positive 5 newtons. Now, how are we going to get the normal force? Well, that's going to be 10 newtons times the cosine of 30 degrees, which is 8 point something, it's either 8.86 or 8.66.
Okay.
8 point,
Okay, Google. What is 10 newtons times the code?
Okay. Alexa,
Let's make it up.
nothing?
Just-
8.66.
Let's-
could you seriously ask what's 10 times the cosine of 30 degrees?
Yeah, probably. Yeah.
Hey Siri.
Honestly, my phone might hit on to say that.
Yeah. 8.66 newtons. So, okay. So, no matter what you do on any inclined plane problem, you find these three forces first, okay? So, gravity always acts
Down.
down, okay? So, if you want to think of this in terms of like an arrow's going, okay, so this one always acts straight down, okay? Okay? Your force parallel always acts, oddly enough, down. Force parallel never acts up. So you got, there's your force parallel. So what's, force normal always acts
90 degrees.
to the surface. So that's always going to be going like this. So you got this action, right? So parallel, normal, force down, right? Okay. So as you go high, as this thing gets towed up, you're going to be going more and more like that, right? Okay. Your force parallel, as you go like that, is going to get, as you go steeper and steeper and steeper, what's going to happen to force parallel? Bigger or smaller?
Small.
Bigger. It's going to go more and more down the inclined plane. What's going to happen to your force normal, though? It's going to get smaller. So technically, if you try to do this as a visual, you'd have a big force normal and a small force parallel. But as you go like this, which is tough to do, your force parallel is going to get bigger, your normal is going to get smaller. Okay. Cool with this. We're good.
Yeah.
Now, initially, there's going to be no friction on the system. No friction.
Don't add it in.
Huh?
Don't add it in.
Oh, we will.
No.
Yeah.
We don't have to.
Yeah, we do.
Are you sure?
Okay. So here's what I want to know. I want to know what's the acceleration of the block sitting on a 30-degree angle with a mass of 1.02 kilograms. And I want to know what's the acceleration. So we've got Fg, we've got force parallel, and we've got force normal. Anything else acting on the system?
No.
So here's the deal. I'm going to set this at a 30-degree angle like this. 30-degree angle. That's it. And I'm just going to let go of it. Whoop! There we go. There's no applied force. There's no friction. There's no squirrels. Nothing. Okay? Just this. Now, get in the habit of oddly enough setting up a chart. So, on inclined plane problems, this is going to be a little bit more complicated, but not bad. So on inclined plane problems, you can still have FAP, okay? So if we put like a rocket engine on this thing, or we have a squirrel pushing it or something like that, right? We can have FAP. We can have applied forces, but we'd have to like physically be doing something to the cart. So in this case, is there any FAP? No, I just let go of it. That's zero. Could there be friction? Oh yeah, oh yeah. There could be friction.
But there's none on
In
this.
this case, that's over. What else can you have?
Force parallel.
Force parallel, right? Now, in the TCS, down was going to be positive. So this is going to be 5 newtons, right? So that's going to be a positive 5 newtons. Is the normal force going to affect this downward motion? No, it's there, but it's not going to affect the motion. So what's the only force that we have left to talk about? No.
Force net.
Force net!
No.
Yes! It's the only thing we have left, right? There's nothing else in terms of affecting this motion on this inclined plane. There's nothing else. Okay? There's nothing else. So, if I take 0 plus 0 plus 5, what do I get? Should be 5 newtons. Now, I'm going to divide that by what?
1.02 kilograms.
1.02 kilograms, and I'm going to get,
A number.
how about, I'm guessing 4.90 meters per second squared.
Can I try Siri?
Our clear.
No. Okay? 4.90 meters per second squared.
You're correct.
So, on a frictionless, changing the angle doesn't change the acceleration.
Oh yeah, it does.
Yeah, because then your force.
Because
parallel.
if you lift it up higher, your force
Oh,
parallel is gonna go
okay. Got it. Okay, sorry.
big. Okay, we good?
Yeah.
Now, go with this. Now I'm going to change it up a little bit. Now the beauty of it is I'm going to go to the exact same problem. 10, 5, normal. Now, listen to me very carefully. I want to know how much force it's going to take to pull this thing up at a constant velocity. So right away, what changes when you see the words constant velocity?
Balance out.
Force normal, is that going to be a factor? Still not going to be a factor. What about force net?
Yeah.
Oh, what's my net force going to equal?
0.
Ooh, right? So because you all are brilliant physics students and you do exactly what I tell you to do, whatever, and you come in here and you can't get your pen to erase because it's being stupid, so you find another way to,
That's a lot of squares.
oh, boy. No idea how that got there.
It's a true piece of art.
Oh yeah.
Okay, there we go.
That looked cool.
Yeah. We'll tell you about that. Okay, so you're going to set up a chart, right? And you're going to go FAP, force parallel, force applied, and,
Wait.
We already have
We
force
already have-
applied.
oh,
at
I'm
the
sorry,
top.
my bad, force friction. I'll make that one force friction.
But
Will
there's
you?
Oh, I hate my pen.
Oh, will you now?
no, but there's gonna be no force friction.
No, we gotta have friction.
But we're on a frictionless surface, so guess what?
0.
There's zero.
Get it out of here.
What's your force parallel?
5.
Positive 5 newtons. But now, so to make this all balance out to 0,
Go ahead,
This
negative
is
5.
negative 5.
my applied force is going to be a negative 5 newtons. So guess what? So if I'm going to set this thing at a 30-degree angle, the force that I have to apply is just going to balance out what?
The
Force parallel.
Yeah, so parallel's trying to keep it down. So I'm going to apply a force that's just going to completely balance that out and keep pushing this up. Now, as soon as I stop pushing, though, and let go, what's going to happen?
It's gonna come back.
Because at that point, what becomes my applied force?
0.
0. This goes to 0. What becomes my net force then? 5 newtons. Guess what? Now you're going to have an acceleration. Got that? Okay. Stop that for a second. Stand up.
Matt, I missed you.
Okay. So now I'm going to turn into the jerk that I am, and now we're going to introduce friction.
Get it? No.
I wouldn't do that to students. So,
Because it's his
still a
job.
30-degree angle. Still the same block. Assuming the gravity hasn't changed. And
Wait a second.
that's 10 newtons. And this is going to be 5 newtons. And here's my force normal
Impressed.
of 8.6. Now I'm going to tell you that mu has a value of 0.2.
Okay.
So here's the million-dollar question. Great. How can I use that coefficient of friction to find my force friction?
Just double check.
Double check.
U, it's mu times Fn. So force, like force N.
Okay?
Good job.
Nicely done, great. So you got mu equals force friction over force normal, true? Now, here's what you're going to do wrong. You mark my words, this is what you're going to do wrong. And you all sit there and go, Mr. Burkhead, we won't do that, whatever. Okay? Here's what you're going to do wrong. Up to this point, you're used to taking mu times force normal, and you're used to getting force friction. Okay? But here's the problem. up to this point, what did you use as your normal force? The 8.66 or 10?
10.
Because up to this point, everything has been on a flat surface. Okay? Everything has been on a flat surface.
Like the tangent.
That is tricky.
Ah, okay.
Do that wrong.
So, this is why it's multiplied by the normal force and not the gravitational force. Because you're only worried about the component of this force that's acting into this inclined plane. So, what you're tempted to do is use the 10 newtons. What's the only situation where you would use the 10 newtons?
You're on a flat surface.
You're on a flat surface, right? 0 degrees. We're not. Now we're on an angle. So you've got to use that 8 point newtons. Okay? That's what you got to use is that 8.66 newtons. So you've got to break the habit of using the 10 newton force. Okay? You've got to break that habit and use that normal force. So you got 0.2, somebody take 0.2 times 8.66.
1.73.
What'd you get?
1.7.
1 point or 2 point?
1
Expecting
1.73?
working through the top.
Correct.
Now,
Yeah.
in the toric coordinate system, is this going to be a positive or negative number?
Negative.
Positive.
No,
She defined down as negative. So
Okay,
that's what
here's
we're
the deal.
just taking down as
Oh.
positive.
Visualize this, okay? I'm here. Now there's friction, okay? Now there's friction. Now, when I let go of it, what's going to happen to the acceleration because there's friction?
It's going to get smaller
It's going to get smaller. Why?
because there's an opposing.
The friction's acting as,
Opposing force.
now when I let go of it, like that, which direction is friction going to act?
The opposite direction of the parallel.
Opposite direction of
Parallel.
motion. So, if I just let go of it, force parallel is going to try and drag it down. My force friction is going to act upward. Now, so in the tori system, if this is 5, this is going to be
Negative.
positive or negative?
Negative.
Negative. That's going to be negative 1.73 newtons because that's acting up, right? Cool with that. Now, when we go to set up that chart, we can have FAP, we can have force parallel, we can have force friction, and we can have finette. So, I've just let go of it. Okay, I held it up, I let go of it. So what's my applied force?
0 newtons.
Yeah, I don't have to worry about that. My force parallel was
8.66.
positive 5.5, right? Still true, still the same angle. Everything's still the true. But now my force friction is going to be negative 1.73. So, here's the deal. You've got $5 to accelerate this block. You got to pay $1.73 to the mafia. Okay? What are you going to have left?
3.27.
3.27?
Yeah.
Positive or negative?
Positive.
Positive. Now, Garrett, how am I going to get the acceleration? What's going to be my last step?
Divided by the mass.
Divided by the mass. So somebody take 3.27 and divide that by 1.02.
3.2.
Oh.
3.21.
Stumbled, man, my disability.
So, what was the acceleration without friction?
There's
4.9, right? That was the acceleration without friction. With friction, what's happened to my acceleration?
It's gone down.
smaller.
It's gone down. Why?
Because
There's an opposing force.
That's acting as
opposing.
opposing force. Good with this.
So can we not combine all of them?
Huh?
What?
Can we not combine all the forces?
Oh no, that's the last problem.
Oh.
Oh, that's the last problem.
So you had that.
I know. Sneaky. Sneaky you are, Greg. Kind of my Yoda voice.
Yeah.
Sneaky you are. Okay.
Or master
Forces, they are strong. Okay. So here's the last problem.
Let's just say the force is within, or, hold on.
Force
Don't.
Have the-
Just stop.
So here's the last problem. I want to push this thing up the incline. Oh, I want to push this thing up the inclined plane at a constant velocity. So, what are the forces that are going to be involved?
Applied force.
My applied force, which is going to act which way, Jones? Up. I'm pushing it up, right?
Parallel force.
Parallel is going to be acting
Down.
down.
And force friction.
Force friction is going to be acting
The opposite direction of motion.
down or up?
Down.
Down. Ooh.
It's a lot of force.
Ooh, that's a lot of force, right? It's a lot of force. Grape asked for it. I wasn't going to work the problem, but now the grapes asked for it.
Well done, great.
Yeah.
Great.
Whoa.
Nice, Logan.
Okay,
This is the one who made a smart kid feel bad.
so here's the setup.
You're gonna use
So I'm going to push it up at a constant velocity. Okay? That's what I'm going to do. Push it up at a constant velocity. So, gravity, oddly enough, is pulling down. My force parallel is still at 5 newtons. My normal force is still at 8.66 newtons. My frictional force, what was the frictional force? 1.73?
1.73.
So this thing is going up. So which direction does my frictional force act?
Down.
Down.
Down. So my force friction is acting down. So which direction does my applied force have to act?
Up.
Up. Is there any way I could push with a downward force and have constant velocity in this situation?
Yeah.
No. No.
No, because then I'd have all positive values, and all 3 positive values can't add up to 0. So I got to have some negative value. So this is a disadvantage of the Tory system, is that like your applied force is going to be negative. That's the only thing that might get a little bit weird for you, but if you stay within the system, you're fine.
Yeah, and like force friction's positive now.
Yeah.
It's like weird.
It's like weird. It's like, whoa.
Yeah, I think
Barry, you're good at
It's like, whoa, we're doing physics. Okay. So we got some applied action going. What else do we got?
We got
force
force.
friction.
Got some force friction action going.
We had some force parallel.
We got some force parallel action.
We got some net.
And finally we have
The net.
The net.
some net action.
Yeah.
But my net action is going to get me.
Zero.
So, this is what I don't know. But I know my force friction is
1.7.
positive or negative, Jones?
Positive.
Why?
Because it's going down.
Because it's going down. And Tori said she wanted down to be positive. Force parallel is going to be 5 newtons, so therefore my applied force is going to be
Negative 6.7.
negative 6.73. And it all adds up to 0, and all is well and right with the book. So that's as complicated as it gets.
You happy with that, Ray?
Okay? Good with this.
My stress ball. Thanks.
That's not my throwing.
Oh my.
I don't have my
Please
right
say the
hand.
camera caught that.
I think it did. I believe it caught Bird's look of disappointment.
It's over there. It's over
Right
there.
hand. It isn't that big.
That's like you weren't even in the right zip code.
Nick, can you really not throw it to him?
No.
Please throw with
He's
your
not
left hand.
Dude,
and
He
prove
makes
that
that
he's
ball look
ridiculous.
tiny. Oh my god.
What do you want me to throw? What do you want me to throw?
Just throw that with your left hand
That
so
should
he
be
looks
your
ridiculous.
finish.
No, to me, because he looks ridiculous.
Burkham.
All right,
That
that's
should be
another
your
chance.
outro.
Hey.
That
Left
should be your
hand.
outro. Whenever you get done with videos,
Yeah,
just
throw a
throw
ball.
the
Throw the
camera
ball? No.
frame.
No, show the like and subscribe
I'm
sign.
not accurate. It's hard.
Here, let's see how good you are with basketball still. Make him the suit.
That's tough to do.
Just hit him with the crotch.
I would have banked that in. Okay, so stop that. Let me hand out the assignment. All right. So let me kind of get you through this. Problem 1 and 2, all you're doing is just calculating values. Do not make any of them negative, just give me the numbers. I'm just making sure that you can plug numbers into a calculator and then make a comparison. Okay, that's all I'm asking you to do. When you get to question number 4, you got a 1.2 kilogram box on some 20-degree hill. At this point, I don't care how you define your system. On number 4, there are no right or wrong answers. I don't care what you make positive and what you make negative. But once you start down that road, you can't change it, okay, within this particular problem. Because this problem 4 goes all the way through number 8. Okay? So I don't care how you define it, but once you start, you can't stop. Okay? Now, notice like on number 5, number 7, number 9, and number 10, there's a little asterisk. Okay, on the back side of this sheet or on another sheet of paper, I want a sketch. It does not have to be drawn to scale. I want a sketch showing all the forces acting on the system. So it's going to look something like this. What are the 3 forces you are always going to have, no matter what? Gravity, force parallel, and normal. When you draw the normal, do not draw that normal pointing straight up. Okay, it doesn't point straight up. It points at a right angle to this surface.
Perpendicular.
Perpendicular to it.
Well,
Yes.
great.
Yay for geometry vocabulary. Okay. So, on those, you're going to label those vectors. Again, it does not have to be drawn to scale, but draw them big enough where I can see them. Okay, you make sure everything is labeled. Okay, so there's that. So, Nick had asked about a story that I told in my first block class that involved a hippo. This is why on the first graph it was a rhino and not a hippo. So, when I was in my time in Africa, I was almost killed by elephants, rhinos, and hippos. The hippos were the closest one that actually killed me. So,
Yeah,
They are the deadliest animal in the world.
Yeah.
well, they are. And so, this is when my dad was over there with me. Dad was, in his early 60s at that time. And we were staying along the Chobe River, and the hotel was a series of bungalows, so it was built up like on stilts to keep it out of the floodplain when the Chobe River would flood. And they had a series of steps that would come down here, so you go up there, and then you've got your bungalow up here. So, it was like 10 o'clock at night. My dad and I were walking along the river, going up to the restaurant there, and we like rounded this corner, and about probably for me to marry away, there was a female hippo who was not happy that we were interrupting her late night snack. Probably her calf was probably in the river, and hippos are very, very, very territorial. So here's the hungry hippo, okay? And here's my dad and I, and she's about 10 feet away from us, and we're about 20 feet away from the nearest bungalow. So, hello. There are 3 bags right up there. Is this for Miss Davis?
Yeah.
Okay, thank you very much. So, get in the bag, whoa! Come on now.
Get in bed.
Gotta get the bags.
Bag
Got the
unsecured.
bag.
Inside joke.
You guys don't understand.
He's jumping all it's not fun.
Do you want me to? Don't make me get up. Don't make me get up.
Get up.
Hey,
Don't make me get up.
Get up, man.
I'll back you up if you get up. I'm sitting right now.
Those bags I'm sitting there. Yeah.
Yeah, you got him, Matt.
Okay. So, back to our story. So, the hippo starts running towards us. You wouldn't think that hippos can run pretty fast, but they can. So, I'm pushing my dad, like literally, like I said, turn my dad, I said, just run. So, Dad's running up these steps. I'm like behind my dad, like pushing my dad up. And literally, I can feel this hippo breathing on my back. And so, we finally get my dad up there, I get up there, and she's not at all happy with New World Order. So she stands down here for about 10 minutes, and I'm Scott, like I could feel her breath because she had her mouth open, and she was like trying to grab my back as I was running. And so she stood there for about 10 minutes and wouldn't let us down. And I was like, well, I don't know what I'm going to do. It's like, we can't. Go away, Cal. But anyway, so yeah, until my dad died, about once a month he would have nightmares about us being chased by those hippos. And so, yeah. Anyway, so there's the first story. Okay, so that's due tomorrow. So here's how this next week is going to play out.
Monday.
Monday we've got a lab to do on inclined planes. And then Tuesday we'll go over that, kind of do a review thing. And then Wednesday is the test. And then we'll start projectile motion Thursday and Friday. So that's kind of the plan. So